already ready. So we can start our laboratory session. Okay. So we can start our laboratory session. So we can start early, 10 minutes, no problem. So sir can discuss a lot of things. Okay. So I'm requesting all of you, please be focus on that. Okay. I think a lot of new thing you are able to understand. Okay. So Bhanuji, can we start now? Yes, please unmute yourself.
Sir, am I audible?
Yes, yes, you are audible now and perfectly visible. Okay, please carry.
Thank you, sir. So thank you to. So first of all, thank you to the committee who have given me the opportunity to say something about the real-time operation. So first of all, myself, Bhanu Pratap Behera, working as a research scholar in NIT Rourkela, also working as a staff, technical staff. So today I am going to demonstrate on real-time implementation, how we'll do, what are the types of real-time implementation are there for the application of our power system, power electronics, all those. So before that, let's share my screen. So I request anybody can confirm whether my screen is visible or not.
Visible.
Okay, thank you. So today's topic is the real-time digital simulation and validation using OPAL-RT platform. So here in this session, we'll just see the OPAL-RT feasibilities in a real-time applications. So before that, we need to know what is the real-time simulation. So real-time simulation means when we are doing the simulation or when we are doing validating or designing some control methodology for a particular plant, we specifically doing a mathematical modeling through the simulation software, maybe your MATLAB, maybe your LabVIEW, or maybe some other simulation software are there through which you have to do the simulation, you have to do the mathematical modeling, and after doing the mathematical modeling or the plant model which is available on the simulation software, you have to just run the simulation through the software, and you need to check whether your control or your according to your expectation you are getting the result or not. So thing is that when you are doing the simulation on simulation software, it is running on your local PC, local computer. So in that case, what happens when you are doing the simulation, that simulation it is not matching with the actual time or actual real time or actual clock, it is not matching. For example, if you have a simulation, you have given some time step. Finally, it is a mathematical model. It has some code. It has to run some time step we should give. So within that time step, if you are giving, and if you in the normal simulation, if you are doing the simulation with the simulation software, in that case your simulation is not matching with the clock. For example, if you are given a time of let 100 microsecond or 200 microsecond, the simulation software will try to solve the mathematics or modeling mathematics there in the model. It will try to solve in the time step, but the time step may be equal to your actual clock or may not be equal to your actual clock. It can, depending on your processing power of the computer, it can process that mathematics within 100 or 200 microsecond, or it can process within less than 200 microsecond or more than 200 microsecond. So it will not match with the actual clock. So it will enlarge the time step. It will try to, once time step, it can take it as a double of your fixed or set time step, or it can be half of the set time step. Like that, depending on your processing power of your computer, it will vary. So that type of simulation, if you are doing, then we generally not called that as a real-time simulation. That is a simulation, but that is not a real-time simulation. When you will implement your controller to a physical hardware for which you have designed the controller, before that we should do a real-time simulation to validate and to check whether the simulation or the control logic is working or is going to work on real time or the actual targets or not. That will validate through the real time simulation. In some cases, the actual target also cannot be created or cannot be made a prototype also. In that case, we should use a real time simulator to validate our control logic. And in some case, in some of the plant, we can make a prototype of the plant through which we can test our control logic also. So in this way, we will see that if you are running through a real-time simulator, then your simulation clock will be matched with your exact time step given on the simulation. So this type of simulation, if you are doing, that will be your real-time simulation, and that is not only on the software. That will be happened specifically based on some hardware will be there, like real-time targets will be there, and through that target you have to do the simulation, and that target will try to match the clock, and if it is matching, then we can say that this is a real-time simulator, and through which if we are doing, that is a real-time simulation. Here you can see, for example, we can say the offline simulation which you are doing through a software, but if we are doing through the real-time simulator, then we can say this is a real-time simulator setup, and the simulation is a real-time simulation. So it will match with your actual clock. If you are given some time step, it will match with that exact in that time step only it has to solve. If it is unable to solve, it will give you the error that within the time step it is unable to solving the mathematics. So if you see what are the different types of real-time simulation, this is one type of real-time simulation which is called rapid control prototyping. Here what happens that your controller model will run on a real-time targets, and you have a prototype model of the plant. So this is like this is a motor which is a prototype, and this is your controller domed on a real-time target. In this way, if you are running or if you are validating your controller, this type of validation is called your rapid control prototyping. Similarly, if you go to another type of validation through real time, that is your hardware in loop. If you are doing the testing or validating through this mode of real time simulation, then what happens that your controller has to run on a real time controlling device. If you are designing the controller for a certain physical plant, then you have to choose certain controlling device. So in that device, you have to dump your control logic, and your plant model will run on the real-time target. Through that, if it is happening in this process, you are going validating your logic, then this is called your hardware in loop. This controller will give the input and outputs to the real-time targets where the plant model is running in real time, and the corresponding plant model output like sensor output and all at a level of control parameters or a level of control logic 5 volt or 15 volt, it will come to the controller, and controller will process it. So this type of simulation is called your hardware in loop simulation or hardware in loop real time simulation. Similarly, another type of real-time simulation which is called power hardware in loop real-time simulation. Here what happens is that if you are doing the simulation or this hardware in loop, this is same like hardware in loop, your controller model will be on the actual controller, and planned model will be on the real-time targets. But thing is that in normal hardware in loop, the plant model will give the signal at a level of control logic. If the controller takes the analog input of say 5 volt, then the plant model will give the sensor output or the voltage current at a level of 5 volt to the controller. If that is happening, this is hardware in loop. But in case of power hardware in loop, it will not give you the reduced voltage or the voltage required for the controller. It will give you directly the voltage which is coming from the plant. If you have a plant of a power system which you have generating a voltage of let 600 volt, then that 600 volt will come directly to your controller through a power amplifier. The power amplifier is it's a part of the real-time simulator. Target and power amplifier are merged and acting as a single device. And the power amplifier will give the voltage, the voltage and current at a level of the plant. Then what happens in the power hardware loop? You have to use the sensors, and from the sensors you have to connect to your controllers. So you can test your sensor modules as well as you can test your controller module both at a time if you are doing through power hardware in loop. So this is called PHIL simulation. So if you see what are the real-time simulator entities who are providing the real-time simulators, the main vendors, if you see, there is a Typhoon Hill is there who are providing real-time targets. RTDS technology, they are also providing real-time targets. D-Space also are there who are providing real-time targets. OPAL-RT, you might know, these are the targets, provides real-time targets. So we will use one of the real-time targets of OPAL-RT to do some real-time testing live in this session. And SpeedGoat also gives the real-time targets, and National Instrument also gives the real-time targets. Now come to the OPAL-RT ecosystem. Our focus into the OPAL-RT. So OPAL-RT ecosystem, what the OPAL-RT provides to us. So first they provide the OPAL-RT, they have the software platform which is the HyperSim, and another is a RT Lab. HyperSim is specifically the software designed by the OPAL-RT team, and this is used for the power system point of application. So if you see in the power system, when they will do the research like multiple bus system will be there, that type of simulation will become easy if you are doing through HyperSim software. And with the real-time targets, you can do the real-time simulation of a power system research. Similarly, if you come to the RT lab, other than that, whatever like power electronics, all those research we can do through the RT lab software. This is the software which is used to interface with the real-time targets, and also it gives some additional facility to do some other type of simulation directly on the RT lab, not on the MATLAB. And this RT lab is integrated with MATLAB. When you are doing the simulation on MATLAB, that is coming that is access through RT lab, and through RT lab will dump the MATLAB code to the real-time targets. Then what are the other ecosystems? That is the OPAL-RT software toolbox. It is there. If you install the OPAL-RT or RT Lab software, then there are the toolbox which will be attached into your MATLAB system. So the toolbox which is EHS toolbox will be there, which is used for power electronics application. If you are using the power electronics where the number of number of the IGBT MOSFETs are more, then that type of simulation if you do directly on the through MATLAB or through using the MATLAB block, if you use the IGBT switch and APG, MOSFET switch which is available on the MATLAB software, through which if you do the real modeling and if you do the real-time simulation, generally it will give you the overruns. Overruns is basically it is a indication that whatever the time step you have given for the MATLAB or for the model, it has to solve that mathematics within the time step. It is unable to solve, it will give the overruns. If it is giving overruns, one means in one time step it is unable to solve. Two means it is giving again at second time step also unable to solve. Similarly, if overruns comes continuously means it is unable to solve. In that type of scenario, if you are using the EHS block instead of the block which is available on MATLAB, then through that EHS block, what happens that you can go in the nanosecond level the time step. You can take the time step into a nanosecond level if you are using the EHS block. There are some other toolbox like Artemis blocks are there, the toolbox designed by OPAL-RT, which will be added onto your MATLAB. And this toolbox are specifically used for power system applications, Artemis blocks. And if you go to e-phasor sim toolbox, this is also used for power system applications. And similarly, Exacta, CPS, these are the toolbox used for communication, who is working on communication protocols like RS485, all those communication protocols, whoever is using, who are doing the research on that, they have to use this type of this toolbox for the research. Then what are the real-time targets or the real-time simulators, the hardware which is available on OPAL-RT? The first hardware, or this is the starting level or compact entry level simulators, which is OP4512. There are OP4500 are there, 12 are there, 10 are there, based on the year they are upgrading the device, but it is the version, it is like OP4512, 113, 10, like that the products are. It is OP4512 generally used on the basic level, like to if you want to test some basic level of real-time simulations, and if you want to do some basic level of rapid control prototyping also, hardware in loop also, that things can be done through these compact entry-level simulators. We'll use this simulator in this session to do the to see the real-time simulations. So here inside this simulator, it is like a CPU, which clock is directly compared with our actual clock, and it has a FPGA inside this real-time simulators. When you are getting the analog out or digital in, or PWM in or PWM out from these simulators, this can this type of this is happening through the FPGA. The processor, when you are giving the code to this real-time simulator, when you are transferring, it is running inside the processor of these targets, and it is communicating through FPGA to outside the one. Similarly, if you see, there is another real-time simulator which is OP4610XG. This is like one of the mid-range version of the real-time simulator in the XG series. And what happens if you are using the XG series real-time simulators? Whatever you can do on OP4512, that the same thing also you can do on 4610. In addition, also it will provide more processing capacity, more CPU core also it provides, as well as it will provides the option to increase the number of input and output ports, for which you have to use another device which is for OP4610 IO module. So if you are using IO module and this XG module once, then you will find that you can increase the IO input up to 128 additional IO you can connect if you use these OP4610 IO devices with the OP10XG. Similarly, this is the high-end simulator 5707XG. When the simulator is becoming higher, then what is happening, that the processing power of the simulator is increased. You can do large mathematics within fixed time step. If it is a simulator at low or the entry level, then if you are using mathematics of your simulation, if it is more, then always it will give you overruns. But if you use this high-end simulator, you can get rid of these overruns, and you can do the actual real-time simulation of high complex models. Similarly, OP5707 also has IO module, which is named as /IO. It can able to increase 256 IO. It can able to increase if you are using through XG devices, then the IO terminal will increase. Similarly, if you come to the another type of the device which is OP8666, This is basically a controller. This is not a real-time device. Real-time is your OP4512, OP4610, 5707. These are the real-time targets. This is the controller. What is there inside the controller? Here the C2000 series microcontroller are there inside this controller, and it is like a development board of this C2000 microcontroller, and it is directly made by OPAL-RT. So what are the digital out and analog in interfaces are directly at a level of real-time target voltage level. Directly from here, through this you can connect to your real-time targets, and you can dump the code onto the C2000, and you can test your you can do rapid control prototyping, as well as you can do the hardware in loop through this controller. This is like a development board for the C2000 made by OPAL-RT or compatible with OPAL-RT real-time targets. So if you see the same TMS board, it is used, and the signal what it is giving analog in and digital out at a level of OPAL-RT or at a level of real-time targets. If you see the real-time targets, what OPAL-RT provides, it is giving the analog in at a level of plus or minus 15 volt. Similarly, analog out also plus or minus 15 volt, digital in out all are at level of plus or minus 15 volt. But if you use directly C2000, you know that this is a logic of 3.3. So then you need some extra circuitry to use the real-time simulator and this C2000 together. But thing is that if you are using this RCP controller, then what happens that directly the output of C2000 will come at a level of 15 volt, and it will come to the real-time targets. Similarly, these are the test benches, which are the combine or the different modules are combined together specifically for a specific point of application. So this is OP1200. This is a test bench which is designed for microgrid modeling, and this is similarly OP1300 for power electronics test benches. In these test benches, your inverters, switches, and real-time targets, power amplifier, all are integrated into one enclosure. So this is a test bench. Similarly, the power hardware loop test bench, here amplifiers are there, PV amplifiers, you can use battery emulators also, you can add through this OPAL-RT test bench. It is a combinedly one set of test bench where all sort of when if you are using a particular application, all sort of devices are integrated into a particular devices. So this is a test bench. There apart from that, so many other test benches are there, but these are the some basic and widely used test benches from the OPAL-RT. Now we'll come to the real-time simulation, how we will do the simulation through the RT lab or through the OPAL-RT targets. So the step, if you see, the first step, generally we should do that. We have to do the simulation through MATLAB. And if you are doing the simulation through MATLAB, then you have to edit, you have to press the edit option available on the real-time RTLab software, and the MATLAB screen will open. You can do your MATLAB modeling, and you can run and check for error. Finally, after checking, you will conclude that your MATLAB model is running. Then after that, you have to come for compilation. In the compilation, what will happen, it will build the model, it will generate the C code of the model what you have generated on the MATLAB, and that C code will be generated in the compile mode, and then it will come to the execute. In the execute, what happens, the C code will be transferred to the real-time targets, and real-time targets will run that code within the time step given on the MATLAB simulation. And after that also we can interact in real time whatever is happening inside the real time simulator. We can see the voltage waveform, current waveform directly on the console section of the MATLAB model. So let's see how to do a simulation. Before that, let's see the hardware which we are going to use. So we'll use these OP4510 simulators for this real-time validation. We will show you the real-time validation on rapid control prototyping, where we'll dump the control logic onto this OP4510, and the prototype plant will be there. Physical prototype plant will be there. That will be outside the real-time targets. This will control the prototype plant. So if you see this OP4510 simulators, this is the front face of the real-time simulator, where you can see this is the power buttons, and this is the buttons for connecting some other modules. This is the buttons for programming the JTAG, means the programming the FPGA, and this is the TXRX to connect some other OPAL-RT in sequence or in series. If you see, these are the backside of the OPAL-RT real-time targets of 4510. Here, these are the ports which is used for analog out, digital out, and analog in, digital in, encoder out. All sort of I/O you can use. The top one consists of I/O, and the bottom one here we have to interface the real-time simulator through Ethernet. So that's why you have to connect Ethernet plug here, and once it is connected to Ethernet, it will be shown on the Attila software. The status should be off. Now let's go to the software interface, Attila software interface. So this is the Attila software, how it looks. That you can see when we'll open the Attila software. This is the version of 2023. Then if you see, these are in the left side, there is a project explorer windows are there, and in the bottom there is a progress window is there. Whatever the task we will do, the progress status will be shown here. Similarly, if you click on this particular device here, the corresponding here we have choose OPAL-RT. One target is connected with this system. So which is the status right now, which is showing up, and the IP address, this much means we are communicating through the network. Hello.
Kaushik, I messaged mailed him also. Then I told my HOD also. Okay, he told
Okay,
he
please unmute yourself. Hello. Okay, Vanuji, please carry on. I'm taking care of it. Vanuji, you are muted. Hello.
Hello. Am I audible, sir?
Now you are audible. You are muted.
Okay, sir. So then this is the software version which is installed on the real-time targets Attila version, which will be shown here. We can use parallelly multiple version Attila software in a single real-time targets. For that, you have to install that corresponding package. Then these are the license given to this real-time targets. Here you can see the number of core. It is 4. So if it is 4 means we can parallelly process our model in 4 different cores, so that within the time step all sort of mathematics can be solved. So if the number of core will be increased, then we can use that number of core to solve our complex mathematical models in the simulations. Then if you see the below, there is a project folder. I named it as a demo, and under the demo there is a model section, and you can add the here right click. If you do, you can make a new model, or you can link the existing MATLAB model. So these are the 2 models I have added for the demonstration. So if you see, there is a plant controller. If you click on the plant controller, it will show you the plant properties of that model. Here, if you see, to do the real-time simulation, first you have to click on edit the model. If you click on edit the model, then corresponding MATLAB model or simulating model will open. There you have to do the simulation, and after simulating or saving the model, you have to come for the set development properties. Here in the set development properties, there is you have to select the target platform, which platform you are going to use. So the if you see the target platform already mentioned here, that is 86 based, OPAL-RT Linux 86 based. So here you have to choose that target platform in the development section. Then in the set development properties complete, then you have to press the build button. When you will press the build button, what happens? The model whatever there, and the if you open the MATLAB model, so it will model will open like this. When you are doing the simulation through MATLAB, we have to, and when you are validating through OPAL-RT, we have to make the model in two subsystem. On the top level, you have to keep two subsystem at least. One will be named as SM underscore the plant, or it can be of any name, but SM underscore has to be fixed. Similarly, there is another subsystem name starts with SC underscore. SC means console. So console subsystem will be there. These are the minimum requirement for the OPAL-RT doing the real-time simulation through OPAL-RT. Instead of SM, we can add, or including SM, we can add another set of subsystem SS subsystem, which is called SM master subsystem and slab subsystem. So SM underscore plant you can make, or SS underscore plant 2, plant 3, like that you can divide depending on the number of core. Here for OP4510 we have 4 number of cores. So 4 number of core means SM will run on a particular core. If you have SS block, it will run on another core. Similarly, 3 SS and 1 SM we can keep on the top level of the model. And in the console, what happens in the console, that this will run console section, whatever there, this will run during the real time simulation. Means when the model will executing in the real time targets, we can communicate to the real time targets on the plant model, what is the voltage, what are the signals are coming on the plant model, that we can get out in the console section, and whatever there in the console section we can view directly on real time. Here if you go to the plant section, these are the plants I have added. So if you see, the plant consists of a 3-phase power source, and then there is a bridge, it is there, which converts our AC to DC. Then we have a inverter which converts again the DC to AC, and this AC is filtered through these LC filters, and then it is going through a line impedance, then it is going connected to a load. This is the simple plant for the demonstration purpose we have created. And you can see the what are the voltage we are giving in the 3-phase power source, that is 450 volt 50 hertz we are giving, and 3-phase power source, and it is converting into DC. We have connected a capacitor here, and this is the universal bridge or the inverters which is we have used, and this is the plant. And the gate pulse which is coming to this inverter, you see, the gate pulse which is coming to the inverter is from the SM group. We have created a module. Here you can see in the plant model that this AF, this sensor measurement block, which is measuring before filter IABC, this is giving the before filter current. Similarly, here through which we are getting after filter VABC and after filter IABC, which is coming here. And if you see the SM group inside the controller, so what the controller we have used, this is like a open loop controller we have used, not we have not used any closed loop controls. So in the open loop controls, what happens that the current after filter and current before filter, voltage after filter is coming. We have taken only, you can see the two line current, two line voltage, not all three we took. we took only IA and IB, similarly I0A and I0B, VAB and VBC, these two only we have taken, through which we are converting that and we are generating three-phase voltages. Here inside the signal conditioning, what you can see that this VAB, VBC, it is coming, then by some doing this mathematics, we are generating the VCA. So another three-phase voltage we are generating. Similarly, because we are using a balanced a load, so we are utilizing this formula. Similarly, VA, VB, VC, we are generating. How we are generating? If you know the line voltage through this formula, you can able to generate VA, similarly VB and VC, and we are clubbing together and using naming it as a VABC. Similarly, if you see there is a IA, IB, and through which you can generate the IC, and similarly IA0, IAB0, you can generate the IC0, and these three IA, IBC clubbed together named as IABC, and here I0ABC, this is the before filter current I0ABC. Then this IABC and I0ABC is coming to here. What happens here? You are converting into VDVQ. So here you can see this VABC is coming, and through VABC you are generating the omega T, and omega T it is going to generate VDVQ. Similarly, it generates IDEQ and I0 IDQ. Through this block we have connected. Similarly, if you come to the power calculation block, here we have used this VDID to generate the to calculate the P VDID plus BQIQ 3 by 2. If you multiply, you will get the real power. Similarly, we will get the reactive power. It will be shown here. And whatever we did here, that you can see there is this is the open loop control. We have a sine wave reference signal which is of amplitude 1 and at a frequency of 50 hertz. Similarly, this is another sine wave at amplitude of 1 and 120-degree displaced. Similarly, this is 240-degree displaced. Altogether, we have added and we are generating the reference duty signal, and that it is you are using this PWM generator block to generate the
हाँ ये पीएचडी है
hello
पीएचडी है एक प्राइवेट यूनिवर्सिटी है सिलिकॉन
Hello.
यूनिवर्सिटी है
hello okay. So here we are generating the pulse, and this pulse, if you see, it is coming to here, and finally this is coming to this inverter. And apart from that, what we have used here, that we told that we can use the analog out of the real-time targets, and we can see whatever is happening on the plant. We can see live the voltages coming from the inverter, VDC, or this before filter current, after filter current on the DSO directly. So for which the signal we are selecting here, and we are giving finally the DSO out, which is going to the analog out block of the real-time simulators. So through this analog out block, it is coming to the DSO, and in the DSO we can see the voltage and current. And you can see here we have used so many, because DSO having, we have only 4 channels. So 4 channels means we should give 4 signals to see on the DSO. And if you are using the DSO, whatever the actual signals, we have to scale down at a level of the voltage of real-time targets. So generally, the real-time target voltage is at a level of plus minus 15. So that's why we have directly reduced to at a level of 10. So 10 by 5000, if whatever the power will come, we will divide into 10 by 5000. Similarly, if you do the Q, similarly to you have scaling down to 1 by 500, we are doing the scaling, and VDC also we are doing the scale down. So everything you have to scale down at a level of 15 or level of 10. Then finally, after doing all the scaling, we are also using the saturation block to limit whatever the signal will come at a level of 15 or minus 15, because the OPAL-RT can give the output voltage at a level of plus 15 or minus 15. So similarly, if you see, if you this is a your multi-port switch, because we, when it will run, we cannot access whatever the things is there inside the SM plant. Only we can access the things is there on the SC. So that's why what we did that here we use a constant which will give the value of, we can select 1 to 7. So if you will give 1, then what happens that this DSO control will be 1. If it is 2, it will be 2, 3, up to 7 DSO control signal will come. And from this console, it will come to the master, which is running on the real-time targets. And when it will come to the master, you can see that the DSO controller, when it is coming, this is the DSO control signals. And if you are giving 1, then PQ, VDC will come across DSO out. Similarly, if you give 2, then BABC, P will come across DSO out. So depending on 3, 4, 5, 6, 7. So this sort of signals will come across DSO out. So if it is coming across DSO out means it will come to the analog out and it will come to the DSO. So in the console section, if you see what we did, that whenever the signal will come from the SM to SS or SM to SC or SC to SM, then we have to use a opcom block, which is the toolbox of the OPAL-RT. If you will use the ActiLab software, this opcom OPAL-RT toolbox will be added, having this opcom toolbox. And similarly, we have used the opcomp here to get the signal or to read the signal from the real-time targets. And this DSO out, whatever the DSO out which is coming to the we can say the analog out terminals, the same also is coming to the console unit. In this scope also we can see the those signals. Similarly, we have used the PQV parameters. Here, this block will show you the P, this will be show you the Q, this will show you the VDC of the plant. And from here, we are giving the inputs, we are giving the modulation index. Right now, it is fixed at 0.8. We can reduce the modulation index, increase and decrease to decrease the amplitude of the inverter output. Similarly, this DSO control, as I told you, have to select the DSO control numbers. So through that the corresponding signals will come on DSO. And this is the pulse control. So if this pulse control will become 0, pulse will not go to the inverter. If it will be 1, pulse will go to the inverter, like enabling and disabling the pulse or to the inverter. For that we have used. So you can see that signals coming from console, it is going inside the SC, and from SM it is coming to the SC. Now, if you come to the ActiLab software interface, like that, in the MATLAB, you have to make the model, and after modeling, you have to run it. You have to run the model, and if you run the model, you can check whether model is running correctly without error or not. You can check the result, like in the MATLAB, we are doing the simulation on this scope. You can see the results directly. So if it is running perfectly on the real-time simulation, what we need to do that we need to build the setup. After doing the editing set, we need to build the setup. When we press building, then what happens that this will generate the C code and corresponding compilation view. It will be shown whatever the status is happening during the building process. Step by step, it will be shown on the compilation view, the display section. And after building, the C code will be generated, the status will be shown here. I will also show that thing also. Then you have to go for the assign target. So here, if you have multiple subsystem like SM plant or SS, some other multiple subsystems are there, you can select the subsystem whether it will run on this target or it will run on some other targets. You can add 2, 3 real-time targets and it will be shown here. Like SM, you can run on one target, and some SS you can run on some another targets. Similarly, we can use 2, 3 real-time targets together to solve your complex mathematical model if it is unable to solve within the time step what you are given. Here you have to select that corresponding devices where it will be executed. Once it is the building process done, the assign task is done, you have to go for the execution task. So in the execution, you have to first set the execution properties. The execution properties, the target platform you have to select, which is you have to select this one because this is the target platform already you have seen. Then if you are doing the simulation, if you are doing the simulation through directly without using the RTLab blocks, means only directly the MATLAB simulation if you are doing and you are dumping to the real-time targets and doing the simulation, in that case we don't need to select the hardware synchronized. In that case we need to select the software synchronized. If you are selecting the hardware synchronized, what happens that the corresponding hardware, like through FPGA you have to interact, like if you are using the analog out blocks or if you are using the digital in blocks, PWM out blocks, anything if you are using the IO terminals if you are using, then you have to use select the properties real-time simulation mode as hardware synchronized. Similarly, after hardware synchronized, these are the fixed setup settings which you have to select, which already selected. Only you have to change this mode of selection, hardware synchronized or software synchronized. After that, you have to go for the load the model. When you press load the model, whatever the C code it is there on the generated in the building process, that C code will be transferred to the real-time targets because already you have selected all assigned the targets here. So when you will press the load, so the corresponding C code will transfer to that assigned real-time targets. After pressing the load button, you have to press the execute button. In the execute button, what happens that the real-time target will start to run the C code. And when it will start to run the C code, the same time your console window will open. Automatically your console window will open, and it will try to communicate whatever signal you have connected from the SM. That output will come to the console and it will be visible directly on real time. So apart from that, if you see what are the toolbox available on the on OPAL-RT after installation, let's see the library browser. You can see there is a Artemis toolbox. These are the toolbox used for the power system point of application. And apart from that, we have the toolbox of RT events toolbox. These are the toolbox which is used in power electronics for generating pulse and logic operators, comparators, these type of filters. If you are using this type of tools, what happens is that your overruns will somewhat will reduce because this tool is specifically designed keeping in the requirement of OPAL-RT targets. So instead of MATLAB toolbox, if you are using this toolbox, your what happens, your overruns will get reduced finally. The MATLAB will able to we can reduce the complexity of your MATLAB model if you are using this sort of toolbox on your MATLAB simulation. You can use this sort of toolbox as well as MATLAB generated toolbox, but if you are using this toolbox, it will try to reduce the complexity of the model. Similarly, if you go to the RTLab toolbox here, as I told, you need to use the opcomp. This is the toolbox will be added in the into the MATLAB software. If you use the install the RTLab software, this toolbox or this opcomp blocks is used to communicate between SM and SS or SM and SC or SC and SM. This toolbox is used, and these are the some other toolbox also are used. You can see this is the monitoring toolbox. If you want to monitor some of the real-time data from the real-time devices, you have to use this sort of toolbox. Similarly, some data logging toolbox also there. If you want to save the some of the files or some of the data into the files directly from the real-time targets into the system, if you want to save some of the data in terms of some files, then you have to use this data logging toolbox. There are some communication toolbox also there, so we can use depending on requirement. Similarly, RTLab IO toolbox are there. So here, whatever the IO devices will be connected, according to that, you have to select the corresponding toolbox. Here only OPAL-RT IO will use, not other IOs. So if you use OPAL-RT IO, then you have to select OPAL-RT. And here in the OPAL-RT, depending on the OPAL-RT model, you have to go for the IO modules. But for OP4510, you have to select the common IO modules. So the IO blocks, which is like analog in blocks are there, analog out blocks are there, data in, data out blocks are there, digital in, digital out blocks are there, encoder in, encoder out blocks are there, event detector, event generators are there. For control, these are the blocks, IO blocks, which is used for OPAL-RT IO interfaces. If you want to interface, like if you want to do the DSO out, if you want to get the sensor signal inside the real-time targets, you have to use the analog in. Similarly, if you want to get the pulse out to the inverter, then you have to use the PWM out or the digital out block to generate the pulse. These are the toolbox. Similarly, RT event toolbox, which is used for machine, which you are working on machine research area, they have to use this toolbox. These are the toolbox, additional toolbox designed by the OPAL-RT software or OPAL-RT team. So what happens that if you use this type of toolbox, your complexity of the model will get reduced, and finally you will get rid of your overruns. So this is about your real-time ArtiLab software interfaces, and this is your MATLAB interfaces. What we should do to do the simulations. Next, we should go for the power electron simulation tools that I shown you already. Next, the demonstration. So next, this is the plant model. If you run, let me run this model. If you run this model, what you can see that we are getting this sort of DC voltage here, 600 something DC volt we are getting, and inverter also generating the pulse. And after that, if you see this waveform, this is the first of all, this is the voltage after filter VABC. This is the after filter VABC. And if you see, then second scope, which is showing the after filter IABC, then another it is your before filter IABC, and another is your VDC, which is running here. The simulation it is running right now. We'll check this simulation into the real time. We are doing right now the offline simulation. Whatever the time step we have given, you can see here you have given the time step TS. When you will do the real-time simulation, you always have to select the fixed time step, which is given right now. Just a second. The time step we have given 20 microsecond. So I have given 20 microsecond as a time step for the entire simulation. So if you do the real-time simulation of this mathematics of or this MATLAB model, what we need to do, we need to edit. Already we did the edit section is completed here. Edit section is completed. Similarly, if you next you have to build after pressing the set already, which is set for the targets, you have to press the build. This plant control, let build the model. You can see just a second, OPAL-RT should be on here. Status is off, no issue. We can build, yes. Building generally it will take time. You can see what are the in the compilation section, what are the things is happening during the building process. Generally depends on depending on the complexity of your model. It may take the building process even 1 minute, 2 minutes, like that it will take, depending on the processing of your system, processing power of your system. This building will also try to adjust the time. Here you can see the current MATLAB version. It is detecting MATLAB version of the model, and the target OS version also it is detecting. And after that, it will what the process it will do to generate the C code. It step by step it will be shown here, that we will see. Building generally takes some time. You can see here some other options are available here. Here on the model section, we have added the model and doing the simulation. Apart from that, there is a IO interface blocks are there. If you are using IO other than OPAL-RT targets, if you are using IO of some other LabVIEW IOs are there, some other IOs if you are using, then this will pop up here. And if you and also this is the OPAL-RT also integrated with LabVIEW, so that in the panel section or in the dashboard section, you can create the LabVIEW front panel window, and you can see the waveform, you can control the plant. You can create a SCADA based window through LabVIEW, and that can be integrated with RT Lab. That can be done through this RT Lab software. You can see here what else it is trying to do, that it is detecting the number of subsystems. It is showing that RT Lab subsystem is 1. So RT Lab subsystem is 1 means it will run on a single core. If subsystem, it will detect 2. If you use SM and SS, then it will detect as a 2. 2 core will be used to process or to run the model. You can see step by step the generating C code for the SM. So it will generate the C code for SM only. It will not generate the C code for SC. SC will run directly on the system. SM C code will be generated. SS subsystem C code also will be generated. Here only we have the SM subsystem. So our building task is completed. You can see completed successfully the building task. After the building, then we'll go for assigning, which is already assigned with the targets available. Then we have to go for the load. You have to go for the load model. You can see model is loading. Loading means it is model is now transferring to the real-time targets. So model is transferred. You can see done transferring file. So whatever the C code generated right now, it is transferred to the real-time targets, and after that it will run. When I'll press execute, the model will run. Before that, you have to see the what is happening on real. Let me open the camera. So you can see that I have already transferred the model to the real-time targets. This is your real-time targets, which is the model is transferred right now, and this is the DSO which is connected to the real-time targets. You can see the analog out. This is the analog out. I'll show you that one. Analog out which is connected, and this is the DSO which is connected. If I press the execute button, what happens that this is the whatever the console, in the console, whatever the DSO control will give, accordingly the output will come here. So let's press the execute button. You can see that we have pressed the execute button. So which signal is coming, that you can confirm from that console. You can see after execution, this console section will open, which will start from upcome. Before upcome, whatever the things will be there will not be visible. And you can see the VDC, it is running on real time, and the VDC it is showing 634. And here you can see we have selected DSO as 2. So 2 means the VA VB VC will come here. VA VB VC is coming. You can see VA VB VC is coming. And if you press similarly the 3 in real time, you can see this is the IA, IB, and IC here as per this. If you press this 4, then it will come this as a your I0 means before filter current, I0A, I0B, I0C. And similarly, if you press the 6, this is the line voltage, which is more than the phase voltage. As you can see, all are sinusoidal voltages. And if you press the 1, which will show you the PQ and VDC. So you have to increase the amplitude. It will be shown. Similarly, if you decrease the modulation index, you can see the voltage output is decreased 0.8, voltage output is increased. So in real time, we are able to operate. This is called real time simulation, but this is not the coming under rapid control prototyping or not coming under your hardware in loop, because everything your controller model as well as your planned model is running inside this real time targets. So now we'll go for this is the hardware setup. Before going for rapid control prototyping, let's see the hardware setups. Here I shown you the OPAL-RT and the DSO. They are OPAL-RT and DSO. They are connected.
Hello. 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 Sir, your voice is not coming.
Am I
Yes,
audible?
it will come.
Yes, yes, now.
You are
Yeah.
audible.
Oh, sorry, it is muted sometimes. Okay, so this is the setup. I have shown you the real-time simulation where the planned model and controller model both is running on the real-time targets, and you are able to see the signals, planned signals on the DSO directly in real time. And right now we will do the rapid control prototyping where our controller model will run on the real time targets and plan model will be outside. Outside, if you see, we have this auto transformer. This is the 3-phase power supply. Then from here, the output is coming to the inside this semicron inverter. We have the rectifier module, which is converting 3-phase AC to DC. Then from this DC, you can see, then from this DC we can convert into AC. If you are giving the pulse, here we are giving the pulse, then it is converting into AC. Then this AC is going to the L filter, C filter, this is combiningly LC filter, then line parameters. Then finally it is coming to this 3-phase variable resistive load box. So this is your plant model, and the controller will run inside this. This is the prototype plant. So in through this, if you are validating your model, we can call this as a rapid control prototyping based real-time simulation. So before that, let's see what are the, you can see here, we have used the breakout boards, which is connected to the corresponding 32 D sub channels. So you can see here, if you use this 1B, we can say from here left side I have shown you that there is 1A, 1B, and 2A and 2B. So this 1B means it is just 1 means a slot, B means your module, and your subsection is 1 or 2 inside this. This is 2 subsection. So this, if you are using this block, this is used for digital output, generally used for PWM generation. So if you are using this first 8 blocks, then it is used as the event generator. You have to use the event at the event blocks to generate the pulse. If you are using this setup for things, then you have to you can use the PWM block to generate the PWM outputs. Here you have to connect this breakout board here, and 0, 1, 2, 3. Similarly, channel 0, channel 1, channel 2, channel 3. These are the outputs we can get from the OPAL-RT. Similarly, this two-way will be used for analog in. The sensor inputs will come to here, and from here through this breakout board, it will go inside this real-time targets. And this is the interface which is used for analog out. This means from here we should get the DSO out. whatever the control signals or whatever the plant signals running inside the real-time target, that will come to the DSO through this analog out. Now, real-time simulation result I have shown you like this. We got in the DSO. I have shown you how we got. Now, through rapid control prototyping, we'll see how we are getting. So let's open the camera and open the lab software. So right now we'll do the rapid control prototyping. So for that, another set of model I have added. Right now the model is running. After running, you have to press the reset button so that whatever the things were running, it is resetted. You can see here it was showing one overrun detected. We have running, but only one overrun. We can able to ignore that. But if overruns is continuous, like 1 lakh, 2 lakh, 3 lakh, then it is the output cannot be the real-time output. You have to reduce the complexity of the model, or you have to use the high-end simulators, or you have to use multiple core to do the real-time simulation if these overruns will come. In the rapid control prototyping, another model I have added where you can see only the controller part is there. You can see not this model. This is the model. So every model, if you run through OPAL-RT, this type of SM_SC, the basic, it has to be there. And inside SM, only controller models are there. No plan models are there. You can see this is the controller model. This is a sensor in like analog in block is used from where sensor are connected. And the sensor right now, it is adjusted and the gain, it is multiplied to get the actual signals. If some DC voltage is there, we have to adjust, shift the signals, and we have to multiply with gain to get the actual voltage. Similarly, in the current also, we have multiplied the gain to get the actual current. Then in the conditioning section, as you have seen already, that we have generating this we have used only two-phase current and generating the third phase. And finally, we are generating IABC, VABC, all three-phase current, voltage, before filter current, and VDC. And we are doing the power calculation VT VQ, and which will be shown here. And as well as we are selecting from the console, because we are using the PWM out block, so we have to select the switching frequency, so which is selecting from the console section. You can see from the console section we are selecting the switching frequency. Right now it is selected as 5000 hertz. And after that you can see we have to select the give the duty information. Duty information is like our open loop output, like what are the sinusoidal output we are generating, that we are giving as a duty for the PWM out block. And whatever the DSO out, it is there, the same thing is here also, it is there, no changes is happened here. So then it is going to analog out. This is PWM out, analog out, and this is the analog in block we have used in the controller. This is the open loop controller, so only this is used. The sensor output is not used to generate the control duties, only directly open loop we have used. And you can see another, I forgot to tell, that if you use this PWM IO blocks, if you use means you have to use this off controller block. If you use the off controller block, then you have to select the bitstream file. So what happens that inside this analog out, I am selecting the data port number 19 here. I am selecting the data port number 12. So based on this configuration file, or based on this bitstream file, this 19 will be decided as the analog out block. So if you see the bitstream file, this is the bitstream file which has to be there inside the project folder of the so MATLAB model. So this bitstream file has a configuration file which bitstream cannot be readable, configuration can be readable. In the configuration file, you can see the 19. If you use the data port 19, then we can use data port 19 where this is use analog out. Similarly, if you use the 12 for PWM out, here it is showing that slot 1 module B subsection 2 it will be chosen. Here slot 1 module B subsection choose. After selecting this port number, this will be selected. So this is the controller is there inside the plant, inside the plant model, and this will run on the real-time targets. Similarly, in the console section, what we can see the P, Q, and VDC, we can adjust the modulation index, we can adjust the DSO control parameters, we can adjust the pulse control, as well as we can adjust the switching frequency. This thing you can do in the console section. So now go to see the rapid control prototyping, how we'll do. In the real time, you can see this is your auto transformer through which you are generating the 3-phase power supply, and this is your load box, 3-phase existing load box. From here we have a sensor module, and you can see here we have the AL parameters, and on the top you can see there is a C is there, and on the bottom there is a line parameters, and this is the semicron inverters, and this is the OPAL-RT, how they are connected. I have shown to you. Now we'll run the model. Already I built the model, so will not take much time to build the model. Model already builded, edited. Only you have to go for the load. If you have already did building, you can do repeatedly load, execute, and reset, load, execute, and reset. So right now I am pressing the load button. So this means what are the C code generated through the build model? It is now transferring. Right now we have generated the C code for the only controller model, like open loop control models. We are generating the C code. Plant models is not there. Plant is outside. This will provide right now the PWM to the inverter. Inverter will run, and the corresponding output will be shown here. Now we'll press the execute button. Now the model is running, but we haven't given any sort of AC voltage. Let me open the console section. You can see on the console section, this is the console section. If you increase the AC voltage, corresponding DC voltage will increase. So let me increase the AC voltage. For that, I need to turn on the power supply for sensor input. Sensor power supply on. Now I will increase the, and you can see here we have to select the DSO as true to note down the voltage. This is the 3-phase voltage. You can see right now we are observing from the plant. You can see this is the 3-phase voltage. It is increasing. We have given the AC voltage so that right now VDC is maintaining at 125 volt, and the load is connected, which is 80 watt. The load is connected, and right now this is the VABC you are observing directly from the plant. And if you select the position as 3, you can see the current. This is the load current which is connected to this inverter. And if you select the 4, you can see this is the current before filter. This is the current before filter, actual current before the filter from the plant. And similarly, you can see if you press you can see the PQ. Here you can see the PQ, because this is a resistive load. Here Q is 0, P only having the some value of 88 watt something. This is the voltage. So you can see if you see the result already I took, and which is on the here. This is the result. This is the result I took from the DSO. So you can see this is the signals which you are getting, and what happens that this noise is due to the you can say the communication, because whatever the wire we are using for the sensor out to the analog out, that wires is not coaxial cable or the twisted pair cable, due to which this noise will come in the sensor module. So through open loop that we have tested and validated, then we accordingly will change the wire, and then we can go for the closed loop. So this is all about the real-time simulation. How we did the real-time simulation through OPAL-RT, and through validated through rapid control prototyping, how we will do through OPAL-RT, that I have shown to you. So this is the presentation or demonstration from my side. So I request the to
Okay,
okay,
thank
sir.
you. Is there any queries from the participant there? Mm, please let us know.
Hello, sir.
Hello.
Can we send more P how many maximum number of PDMs can be sent out from OPAL-RT?
See, OPAL-RT, whatever the device we are using right now, we can use 4 sort of digital out. So if you use the PWM out, you can use the only 8 PWM out you can generate. And if you use the digital out block, then you can generate 4, means your 32, 8 into 4, 32 digital out you can generate. But if you use the PWM out block, then you can use only 8. But if you use the digital out block to generate the PWM, you can use the 32. And if you want to use more PWM out, then this OP4510 is not enough. You have to use the XG model OPAL-RT with IO module, which will expand your IO up to 128 PWM.
Okay, sir. Thank you.
Thank you.
Is there any other query? Any other queries? Okay, I think there is no other query from the participant end. Okay, thank you, Bhanuji, because the presentation is very good and you have shown a lot of things how to integrate that, how to integrate the experimental setup with the OPAL-RT and how to generate the pulses. Okay, and what are the basic idea, how to simulate, how to build, everything you have discussed so elaborate manner. I think it will be very helpful to them. Okay, thank you again for giving your valuable time. I know that you are also very busy. Okay, different activities in departmental as well as laboratory. Okay, thank you again for giving your time to us. Okay,
Thank you, sir. Thank you.
you're welcome. So good evening, all the esteemed participants. So the our laboratory session has completed. So we can